Last time we talked about if you have a linear transformation. Again, I'm just going to, for now, talk about linear transformations from R2 to R2. And so if we have a linear transformation, we saw that we could write it as a matrix. I better avoid using X, but let's say T of V is AV, where there's a few different ways to think about this. You can think about this matrix as so this transformation of the vector V. The output is multiplication on the right by this vector V, or multiplication on the left by the matrix A, however you want to say it. Or if you want, you could think of T of V. Let's write V as a vector in x2, say xy. So T of xy you could think of as the output just generically being ax plus by, cx plus dy. And again, you can think about that as a, b, c, d times the vector xy. So there's really two different ways to think about this. You can just either think of directly the rule that you have for what's T of xy, where xy is your vector in R2, or you can again explicitly just appeal to writing T of V as some matrix A, capital A, times the vector V, right? So this would be, I'm really just saying T of V is equal to AV, where A is your matrix, lowercase a, b, c, d. So two different ways to think about linear transformations there. What I said last time was that if we know where the standard basis vectors 1, 0 and 0, 1 are told to go, so if T of 1, 0 is AC and T of 0, 1 is BD, so if it's that vector in R2, then this is exactly the transformation that we would get. So this is actually a two-way street. We know that if our transformation is of this form, then our basis vectors 1, 0, and 0, 1 get sent to AC and BD. On the other hand, we know that if our basis vectors get sent to AC and BD respectively, then this is our linear transformation. So it's really, I'm kind of thinking about two different sides of the same coin here, but it's really just a dictionary to go back and forth between thinking about our linear transformation in terms of a matrix or in terms of just understanding what this does to the standard basis vectors. And so just as an example, let's see if we can find the matrix T that's going to map R2 to R2. And I want to find this matrix corresponding to rotation counterclockwise by 90 degrees. So I want to figure out what is this rotation by 90 degrees. So I want to figure out what is the transformation so that if I have any vector that I want, say some vector v, okay, of some particular length. So if I have some vector v, I want to figure out what is the transformation that I have to apply to v, so that v gets mapped to the same vector, just rotated. Let me try that again. Just rotated 90 degrees, so that the angle between them is about 90. So I want to think about what is the transformation that's going to take our vector v to this green vector, to this red vector, T of v. Okay, so we want to think about what is that transformation T that does that. And it turns out all we really have to figure out is, we know that if we take the vector, all we really have to figure out is what's the transformation that's going to take the standard normal, the standard unit vector 1, 0 to this vector 0, 1, and likewise, I'm going to have to draw over this in just a second, but likewise, what's the transformation that's going to take the green vector to that green vector, right? So I'm trying in each case to rotate our vector 90 degrees. So this orange vector gets put up there. The green vector gets put down here. The blue vector, again, everything's just being rotated 90 degrees. So that's what we're trying to figure out. What's the transformation that we can apply to our vectors in R2 that's going to correspond to rotation 90 degrees in a counterclockwise manner? Okay, so what we need to figure out is what's t of 1. So we don't know what this transformation is. That's what we're trying to figure out. But we do know what's t of 1, 0, and what's t of 0, 1. And again, for the reasons that we talked about before, by linearity of the linear operator t, and by the fact that 1, 0, and 0, 1 is a basis for R2, if we know those things, we know everything. We know everything about the linear transformation. We know where any vector sends any other vector. Okay, we have a complete map. So we need to figure out, we know that this orange vector, 1, 0, is going to get mapped to the vector 0, 1. Okay, so that corresponds to, I wish I could animate on this thing, but that corresponds to sending, let me actually do it this way at the risk of, I don't want to over clutter that graph. So let me just redraw that graph very quickly where we just have V and where V gets mapped to. Okay, so this is V, and this is T of V. Oops. This is T of V. And this is a 90-degree angle between them. Okay, so the first thing we were trying to figure out is if we were talking about rotating by 90 degrees, we need to figure out if we take our vector 1, 0, that's going to get mapped to 0, 1, right? So that's going to be our, that's going to be what the map is. So that's t of 1, 0 is going to be 0, 1. On the flip side, if we look at our vector 0, 1, so that's our other basis vector. Forget about the fact that this vector and this vector are the same. That's a coincidence. What I mean is that that's not going to be true in general. All we want to know is what happens to our input basis vectors, 1, 0, and 0, 1. And so 0, 1 is going to be this vector, and that's going to get moved to this vector over here. And that vector is going to be the vector, let's think about what it is. So this is -1, 0. And so it turns out that if we know these two basis vectors, then we know everything. And in fact, T of V is going to correspond to multiplication on the left by the matrix A, where the columns of A are determined by those columns, the outputs, right, the images of the basis vectors T of 1, 0, T of 0, 1. Okay, so T of V is going to be this matrix times V. To say it another way, or if I wanted to just not write this as a matrix, I could say that the vector xy is going to get mapped to -y, x. Okay, and it turns out that those two vectors are always going to be perpendicular to each other, or we'll say orthogonal. Okay, we'll use the word orthogonal later. Okay, and so that gives us our 90-degree rotation. Okay, so that's one example. So what I want to do is I want to do this again. And what I want to do is I want to find the matrix T corresponding. So let me just emphasize here that we're still just talking about from R2 to R2. But I want to find the matrix T, taking a vector from R2 to a vector in R2, corresponding to a rotation in a counterclockwise manner by some angle theta as measured in radians. Okay, so I want you to think about So I want you to think about the following. So we have R2 with our vector v. V can start wherever you want, doesn't matter. Okay, so here's our vector v. And what we want to do is we want to figure out, for some angle theta, we want to figure out maybe our theta is something like that. These are supposed to be the same length. That's a little bit too long looking. So it looks just a little bit too long. But let's say that that's t of v. And so we want to figure out what's going to send this green vector. So what's going to send this green vector to this orange vector. Okay. So that's what I want to know. Okay. And here the difference between the two, the difference between these two vectors is that angle theta. Okay. So that's a job for you. We'll talk about it in the next video.